discuss about abnormal colligative properties and abnormal molecular weights. First of all, before going to abnormal molecular weights, also I would like to tell you here is that the very purpose of colligative properties is main application of colligative properties is to find the molecular weights of unknown solute, because you take any colligative property, if you take vapor pressure, then P naught minus P s by P naught is equal to mole fraction, and this mole fraction of solute is equal to weight of solute by gram molecular weight of solute divided by weight of solute molecular weight of solute into weight of solvent by molecular weight of solvent. So, in this weight of solute, that is how much solute is added in what weight of solvent is known, that is what is the solution that we take. So, we know the weight, but what is the solute given, that is not known. Then in that case, using this you can determine the molecular weight of solute. Solvent weight is known, molecular weight is known. For example, if it is an aqueous solution, then in how much water? Say 1 liter, that means density is 1, so 1000 grams, right. Molecular weight of solvent, that is 18, so that is 54.5. So, you are given some unknown solute of 5 grams, so you have added 5 grams. So, weight of solute is 5 grams, then molecular weight of solute you can determine. And if it is elevation in boiling point, again the same thing, delta Tb is equal to Kb into molality. What is the elevation in boiling point? By experimental method one can determine the delta Tb. Then using the term molality, that is equal to Kb into weight of solute by molecular weight of solute into 1000 by weight of solvent. So, again what weight of solvent? Say 1 liter of aqueous solution. This is, then in this case weight will be again 1000. What solute is added? How much is added? Say again 5 grams. So, you know this, then you can determine molecular weight of solute. Kb of water is known, that is a constant value, as I already we told us in the previous class that it is 0.52, which is a constant value. So, experimentally if you determine the delta Tb value or vapor pressures of the solutions and all, again similarly depression in freezing point, delta Tf is equal to Kf into molality. Osmotic pressure, pi equals to Cst, where C is the molar concentration. So, ultimately take any colligative property, measure the property, measure the vapor pressure of solution, measure the boiling point of the solution, or measure the freezing point of the solution, or measure the osmotic pressure of the solution. Any one colligative property you measure experimentally. From the experimental values, then you take this and determine the molecular weight of solute. So, that is the main application, right. But why I discuss this here under this is about to discuss about this abnormal colligative property and abnormal molecular weight. What happens is the colligative property what you measure, suppose you have measured experimentally delta TB value. This delta TB value what you measure experimentally will be different from the theoretically what we calculate using this equation. Suppose you know that the solution is 1 molal, the solution is 1 molal, suppose you know. For that 1 molal solution, now using this equation you will calculate. Suppose if it is 1 molal aqueous solution, then Kb value is known. What is the Kb value? Kb for water is 0.52 Kelvin kg per mole. Therefore, for 1 molal aqueous solution of salt, delta TB will be Kb into molality, that is equal to 0.52 into 1, which is equal to 0.52. But experimental value may not be 0.52, either it may be greater than 0.52 or less than 0.52. So, what is happening? That theoretically you are calculating it as 0.52 for a 1 molal aqueous solution of solute, the elevation in boiling point, but experimentally what I am saying is, in all 1 molal solutions what normally we take, you may not get the value of elevation in boiling point as 0.52. That value, experimental value, what we determine, either it may be greater than 0.52 or less than 0.52. Why? What happens? Why you are getting the difference? The reason being that, again it in turn relates to that molecular weight of solute what we are taking theoretically. For example, you take acetic acid or you take benzoic acid in benzene. I am taking benzene as a solvent, that is a very good example. So, I am taking it. What happens is, the molecular weight of acetic acid, which is normally the acetic acid molecular weight, which how much is the acetic acid molecular weight? That will be around, as you know, CH3COOH is the formula of acetic acid. So, it is carbon, 2 carbons, it is 24, 2 oxygens, 32, 4 hydrogens. So, it is 60. You will take molecular weight of solute as 60, provided, again I am repeating, acetic acid, if you take it in benzoic acid or benzoic acid in benzene, acetic acid in benzene, non-polar solvent. What I mean, acetic acid if you take it in benzene, then that benzene weight, how much weight of benzene you are taking, molecular weight of benzene, you know, weight of solute, this acetic acid what weight you are adding, you know, molecular weight of acetic acid, you know, everything that you know. Like using that, if you calculate, you are supposed to get 0.52, but you do not get it as 0.52. The reason being that molecular weight of solute which you are taking it as 60 will not remain 60 in solution. Why? What happens? What happens is that acetic acid undergo dimerization in benzene. So, as a result, what will form is a dimer. When a dimer is formed, what is a dimer? That I will show it now. A dimer is that 2 acetic acid molecules are combining, form a dimer. That means, earlier what you are considering as 2 different molecules of acetic acid will now become one single molecule of a dimer. So, as a result, what will happen? The molecular weight doubles, it becomes 120. Does it mean that can we take 120? Again, no. What is the extent of dimerization? Whether the entire quantity gets dimerized, only partial. It is like dissociation. It depends on the degree of association or dissociation, right. Now, so this depends on the molecule. molecular weight of a solute in solution depends on whether it is undergoing any association or dissociation. If solute undergoes any association or dissociation, then the observed molecular weight will be different from theoretically calculated molecular weight. Means experimentally observed molecular weight is different from theoretically calculated molecular weight. So, when the molecular weight is different, obviously colligative property also will become different. So, finally, the conclusion is that your observed colligative property is different from theoretically calculated colligative property, and observed molecular weight is different from the theoretically calculated molecular weight. So is the reason that as if one of it changes, the other one also changes. That is what our meaning here, abnormal colligative properties and abnormal molecular weights. Then how to correlate these two? For this, we introduce another term called Van 't Hoff factor. Now, we will discuss what exactly the dimerization, how it takes place, what is this Van 't Hoff factor, then how to relate this theoretical and experimental values. Now, we continue. So, this Van 't Hoff factor relates to the extent of association or dissociation. So, as I told you in the case of this benzoic acid in benzene, benzoic acid in benzene, if you take benzene or any non-polar solvent, what happens that C6H5COOH is the benzoic acid formula, but in benzene what happens is this benzoic acid undergoes dimerization, means two acetic acid molecules come closer, will form a cyclic ring dimer. This is the dimer. So, chemically you will show that 2C6H5COOH in benzene solvent becomes C6H5COOH twice. So, here two benzoic acid molecules are uniting to form a dimer. So, the molecular weight of this, as you can see, this whole thing will now become act as single molecule with molecular weight of 120. Actually, here the molecular weight is 60. So, in benzene it is undergoing dimerization. As a result, the number of molecules is getting halved. So, if you start with suppose 1 molal, if you are starting, now due to dimerization this decreases to 0.5 mole due to dimerization. Assuming alpha is equal to 1, that means degree of dimerization is 1. All acetic acid, benzoic acid molecules, if they are getting converted, getting dimerized, then it becomes, well, anyhow, here this is acetic acid instead, it is the molecular weight 60, and then the dimer molecular weight is 120. For benzoic acid, of course, it is different. So, like this, if you take, due to dimerization, number of moles is decreased. When the number of moles is decreased, your molality also decreased. When the colligative property is a property which depends on the concentration. So, when the concentration is changed from 1 molal to 0.5 molal due to dimerization, obviously colligative property changes. This is what is abnormal molecular weight and abnormal colligative property. Then to overcome this, Van 't Hoff suggested a correction factor by taking that all the colligative properties to equalize the theoretical and experimental colligative properties, a correction factor called Van 't Hoff factor I is introduced. Okay. Then how it is introduced, how it is incorporated in all the equations, then how do we do the calculations, and how this Van 't Hoff factor relates to degree of dissociation or degree of association, that next we are going to see. Let us consider the Van 't Hoff factor. What is this Van 't Hoff factor? Van 't Hoff factor I is equal to the ratio of your theoretic calculated molecular weight of solute by observed molecular weight. Calculated or theoretical molecular weight of the solute divided by observed molecular weight, which is otherwise also equal to the observed colligative property by theoretical or calculated colligative property, because colligative property is proportional to concentration. Therefore, colligative property is proportional to 1 by molecular weight, because concentration is inversely proportional to molecular weight. So, here you can see that I is calculated molecular weight by observed molecular weight, which is equal to inverse in the case of colligative properties, that is observed colligative property by calculated colligative property. Now, this is what we take it as Van 't Hoff factor. Now, this is incorporated in equations of colligative properties as that the in case of vapor pressure, relative lowering of vapor pressure of a solution P naught minus Ps by P naught is equal to I into mole fraction of solute. Elevation in boiling point delta Tb is equal to I into Kb into molality. Depression in freezing point delta Tf is equal to I into Kf into molality. Osmotic pressure is pi is equal to I into CRT. So, as you can see, in every case the actual value we are multiplying with this value of I. This I is what we call Van 't Hoff factor. So, if you introduce this I, incorporate this I, or rather you multiply the whole value what you are getting with this correction factor, you will get the actual value of the colligative property. Then if you do the calculation like this by taking this correction factor, then your this calculated value and experimentally observed value both will become same. So, this is a correction factor. Now, how this correction factor relates to degree of dissociation or degree of association? That means alpha. In case of solute undergoing dissociation, how to calculate this I, and in case of solute undergoing association, how to calculate this I. How this I relates to that degree of association or dissociation alpha is what we see it in the next discussion. Now, take the case of solute undergoing dissociation. Consider a solute AN undergoing dissociation to A, means AN dissociates to Na. Initially, if you start with 1 mole of that AN, which undergoes dissociation by alpha moles out of 1 mole, that means nothing, alpha is nothing but degree of dissociation. So, this will become 1 minus alpha and this will become N alpha. Initially, this will be 0. Now, total number of moles at equilibrium is equal to 1 minus alpha plus N alpha, which is equal to 1 plus alpha into N minus 1, right. Now, Van 't Hoff factor I is equal to number of moles of solute after dissociation by initial number of moles. Which is equal to, now what I am writing here is this Van 't Hoff factor I is equal to number of moles of solute after dissociation. What is the basic reason for colligative property to change from theoretical to experimental? Because the solute is undergoing either association or dissociation. That means there is a change in number of moles of solute before and after association or dissociation. Before dissociation, you have 1 mole of solute. So, your colligative property before dissociation, colligative property, for example, osmotic pressure pi is equal to CST, that is equal to 1 into ST. After dissociation, pi equal to 1 plus alpha into N minus 1 into ST, because after dissociation there is a change in number of moles. Initially you have only 1, assuming that volume of solution is 1 liter. So, 1 mole in 1 liter, this becomes 1 molar. So, it is only ST, but now it is 1 plus alpha into N minus 1, this many number of moles are increased. Due to dissociation, number of moles in solution is increased. As a result, actually the colligative property is changing. So, that if you write it over here, after dissociation it is 1 plus alpha into N minus 1 and initially is of course 1. Therefore, from this what we can write is I equals to 1 plus alpha into N minus 1, and from this also what I can write is I minus 1 is equal to alpha into N minus 1, means alpha is equal to I minus 1 by N minus 1. This is the relation for alpha and I. If you are given I, what you can determine is degree of dissociation of that solute. Alpha is equal to I minus 1 by N minus 1. Using this colligative property, so you are able to understand alpha, you are able to determine alpha. In case of weak acids, like again acetic acid in water, benzoic acid in water, any such weak electrolytes, weak acids or weak bases if you take, where using this colligative property you are able to determine alpha, and if once you know the alpha, in case of solutions of weak acids and weak bases, from colligative properties alpha can be determined. So, what also you can determine is pH of solution can also be determined, because in the case of weak acids in the ionic equilibrium we know weak acid solution of weak acid, pH is equal to half pK minus half log C. So, for that what we require is alpha. So, if once you know the alpha, what you can determine is Ka value, and if once you know the Ka value, you can determine the pH. Same is the case even for weak bases, and even solubility product of salts also can be determined. For a sparingly soluble salt like AgCl, this alpha is nothing but the solubility. So, from that you can determine the solubility product, right, or from the solubility product if you know the alpha, then what you can determine is its colligative property, or if nothing of, if any one of it is experimentally determined, what you can determine is a molecular weight of the unknown solute. So, like this one is interrelated to the other. So, this is the relation for alpha and I in the case of solute undergoing dissociation. Here due to dissociation number of moles is increasing. So, you are getting this kind of picture. So, as the number of moles is increasing, you will get certain deviation in the colligative property. But instead if the solute undergoing association, the next case what we discuss, association. In the case of association, the total number of moles after association will decrease. So, the observed colligative property will be in a opposite inverse of what you are observing in the case of dissociation, right. So, then how to relate alpha and I in the case of association is now what we continue. Now, we go to the case 2. Association. The earlier thing, dissociation, is basically applicable for electrolytes in aqueous solutions, acids, bases, salts, which will undergo dissociation. And as already previously we discussed, like benzoic acid in benzene, acetic acid in benzene, in some cases solute also undergoes association. That is what happens in the case of polymerization process. What is a polymer? Many number of monomers getting added up to one another to form a long chain of polymer, right. So, that is association. In that case what happens? If you start with, in order to form 1 mole of a, polymer, you have to take n moles of solute in the solution at the beginning. All that one gets added over to the other, and then you will get a long polymer. So, obviously there will be a huge change in the concentration. Suppose if 1000 molecules are adding up together, so you will take 1000 moles of monomers to get 1 mole of a polymer. So, concentration obviously becomes 1000 of the initial concentration, 1000th part of, if you take 1 mole, then after association it will become 1 by 1000. So, there will be a huge change in the concentration. So, when there is a huge change in the concentration, obviously also there will be a huge change in colligative property, and also there is a huge change in molecular weight. Okay. So, coming to the case of association. So, again consider n moles of solute A undergoing association. So, Na giving An, initial, again let us take only 1 mole, 0, at equilibrium it will become 1 minus alpha, then how much of this you will get? Alpha by n. Therefore, total number of moles of solute, after association is equal to 1 minus alpha plus alpha by n, which is equal to 1 plus alpha into 1 minus 1 by n, right. Therefore, Van 't Hoff factor I is equal to number of moles after association by initial number of moles, that is equal to 1 plus alpha into 1 minus 1 by n by 1. Therefore, alpha into 1 minus 1 by n is equal to I minus 1. Therefore, alpha is equal to I minus 1 by 1 minus 1 by n. So, this if you look at it, alpha is equal to n into I minus 1 by n minus 1. This is in the case of association. In the case of association, alpha, that is the degree of association, is equal to n into I minus 1 by n minus 1. So, either in the case of association or dissociation, finally you can determine this alpha like this, or if you know the alpha, you can determine I, from which finally you can have idea on the colligative property. And if once we got an idea on the colligative property, then what we can determine is the actual molecular weight of solute in solution even after its association and dissociation, right. But the whole main purpose of all these colligative properties we have different applications, as in every case that I discussed the applications, and common applications of all this is to determine the molecular weight. Okay. So, this is about the abnormal molecular weights and abnormal colligative properties.